Теперь у нас доклад на английском, и я представляю вам Mauro Tempesta from Italy, Технический университет Wien.
So, hello everybody. So my name is Mauro. I'm part of the Baccaro tour team, and during this talk we present a technique that is used to fortify the security of web protocols by using browser-side security monitoring. And this is a work that has been done in collaboration with my former colleagues in Venice, Stefano Calzavara, Riccardo Cardi, and the university where I'm currently working at, so TU Wien, with Matteo Maffei, Marco Squarcina, and Clara. I'm really bad in German, so I'm not saying the first name. So, let's start by having a look at what a web protocol is and what it looks like. So essentially, web protocols are protocols that are built on top of HTTP, HTTPS, and they are typically used to implement authorization or authentication features like single sign-on. And here I propose you a small example. Probably you know the website I want to connect to. It's CTF Time. But since I hate to create a different account on every website, I want to authenticate on that site using my identity on a different website, like in this example, GitHub. So what do? I go to the login page of CTF Time. I click on the enter using GitHub link. Once I do that, CTF Time is redirecting me to GitHub. And here I'm presented with a form where I have to provide my credential, username and password. Once I've done this, I get redirected back to CTF Time, and I'm automatically authenticated there. So, in this, this is a simplification of a protocol which is called OAUTH2. And in this context, we call CTF Time the relying party, or RP for short. And GitHub, which is verifying my credential, is the identity provider, or IDP. So, by looking at this simple protocol, you may think that there is nothing that could go wrong, right? Well, actually, no, that's not true. In fact, designing and implementing web protocol is really hard, as witnessed by the huge number of vulnerabilities that have been presented during the last year at the top-tier security conferences. And what's the underlying problem? Why is it so difficult to secure web protocol? The problem is that the browser is not aware at all of the existence of web protocols. So it doesn't know when the protocol starts. It doesn't know when the protocol ends. What are the messages that are part of the protocol? What is the expected order of these messages? And it doesn't even know whether you would like to ensure some confidentiality or integrity guarantees on the contents of the communication. So our proposal is to extend the browser with a lightweight security monitor that enforces the compliance of the browser behavior with the protocol specification. We have implemented our technique in using as a Google Chrome extension, but in principle you can do it on any other browser. And the advantages of our solutions are twofold. First, users of vulnerable websites are automatically protected on all against a lot of different kind of attacks. And second, the specification for a certain protocol can be written just once and enforced in a uniform way on all the websites that are relying on that protocol. So first of all, we have to identify what are the security challenges that we must face for securing web protocols. And essentially they are the compliance with the protocol flow. That is, we want to preserve the intended sequence of messages that are exchanged by honest participants. And moreover, we want to perform some kind of integrity checks on the contents of the protocol messages. And the second, we want to ensure the confidentiality of some message components like credentials or tokens or something that in any case must be protected and revealed only to the intended parties. So how do we do this in WPSE? So essentially, for every protocol that we want to support, we have to write down a protocol specification where we describe the structure and the order of messages. With structure, we mean whether there are certain parameters, certain HTTP headers, and so on and so forth. And Apart from this, we also want to specify what are the desired security policies for the protocol run, both in terms of confidentiality and integrity. And how does it work in WPSE? Essentially, what we do is that protocol messages are blocked, either if they're not in the correct order, or there are some integrity constraints on the messages of the protocol that are not satisfied. An important thing is that we always allow protocol-related messages, and this is important to ensure the website functionalities, because while running the protocol, the website may do some requests like fetching resources, which are not protocol-specific, and they're needed to ensure the correct functioning of the website. Regarding the secrecy of message components, what we do is, when we see secrets in incoming messages, we replace them with a random placeholder before they enter the DOM of the page. And we replace these placeholders with the appropriate value only if the message is sent to an origin which is entitled to learn that secret. And why do we want to prevent secrets from flowing into the DOM? Essentially because once the secret is into the DOM, it gets available to any malicious JavaScript which could be embedded into the page. In that case, we have lost. So let's see a bit more in detail how the OAuth 2 protocol works. Essentially, this is what I shown you before. The part from 1 to 4 is what I shown you before. And the remaining part takes place only between the relying party, CTF time, and the identity provider, so it's out of our control. OAuth 2 has some important parameters that are used for its correct functioning, and these parameters are what I call here RPID, is the identifier of the RP at the identity provider. So it's in this case, it's the identifier of CTF time at GitHub. Then we have the redirect URI. This parameter is a URI where the user browser must be redirected after completing successfully the authentication. We have a state parameter, which is optional, and it's used to prevent login cross-site request forgery attacks. And in the step 4 of the protocol, we have the authorization code, which is a secret that is issued by the IDP, and which must be communicated to the relying party, so CTF time, in order to redeem an access token, which is used in the later steps of the protocol, in order to access the user resources or the user identity at the identity provider. And moreover, in step 4, we also have the state parameter that was communicated at step 2. So how does a WPSE policy for this protocol look like? Well, essentially, regarding the protocol flow, we are just saying that the messages of the protocol should have the form of the messages 2, 3, 4 that I've shown here in the slide. And as an integrity guarantee, we require that the redirect URI and state parameters are the same in message 2 and message 4. Regarding the confidentiality policy, we are just asking that the authorization code and the state parameter are secret and only shared between the relying parties, so CTF time, and the identity provider, GitHub. So this seems a really simple policy, but it's already pretty effective at preventing real attacks. And let's have a look at this one, which was presented in 2012. And here, the goal of the attacker is to force the user browser into authenticating under the attacker's account, so not using his own account. And it works like this. So the attacker starts the protocol and authenticates using his credential and obtains a valid authorization code. Then suppose that for some reason I'm contacting the attacker website, maybe because he's hosting a website with the torrents of my favorite TV series, and instead of providing me torrents, the attacker is redirecting me to the redirect URI of CTF time. And this message includes the authorization code that he obtained previously. What happens is that subsequently, CTF time continues the protocol flow with GitHub, and the overall result is that I'm forced into the attacker's account without noticing. And Why is this issue solved by WPSE? Essentially because our monitor detects that the message with the shape of message number 4 in the protocol is being performed without having performed the previous steps. So the message is out of order and therefore blocked by our extension. Let's have a look at a different example regarding the confidentiality of secrets. And this attack is called the state leak attack. So here I'm running my browser and performing the protocol flow normally. Now suppose that for some reasons the page at the redirect URI is embedding some contents, for instance an image or a script, from the attacker's website. What happens is that the authorization code and the state, which are part of the URL of the page, are leaked to the attackers through the referrer header. If we are running a browser protected by our monitoring technique, we have that the attacker, instead of receiving the real secrets, is just receiving the random placeholders, because when the message is sent to the attacker's website, our monitoring technique detects that the attacker's website is not among the origins that are entitled to learn the secrets, so it doesn't replace the placeholder with the actual values. We did an experimental evaluation of the wild of our solution by trying to authenticate and use 90 different websites taken from the Alexa top 100K, and we focused our attention on just 3 identity providers, the most famous ones: Facebook, Google, and VK. And we have analyzed both the authorization code mode of the protocol, which is the one that I've just shown you before, and the implicit mode, which is a simplified variant of the protocol. What we found out in terms of security is that there are on 4 different websites leakage of sensitive data, like the access token, because of the presence of advertisement libraries that are taking the entire URL of the page and sending it to some of their services. And we also noticed that 55 out of 90 websites are lacking or are using in an improper way the state parameter. So they're essentially vulnerable to login cross-site request forgery attacks. We limited ourselves just to attacks that can be performed that can be detected just by browsing the website, and the fact is that we didn't want to actively attack them. Regarding compatibility, we have had problems due to security critical deviations in the protocol flow on 7 websites. For instance, the authorization code was sent twice, and the second time over HTTP, so even broadening the attack surface that is of the protocol. Besides OAUTH, we have decided also to try to model different protocols like the SAML to see whether our technique was expressive enough to cover most of the existing web protocols. And we found out that the Google implementation of SAML2 is vulnerable to an attack which is similar to the session swapping that I presented before. And this attack allows you to be authenticated on Google Suite applications like Gmail and Google Drive within the attacker's account. And this is particularly bad because if you're authenticated in the attacker's account, then every search you do on Google Engine is saved inside the attacker's account. If you're storing something on Google Drive and you don't pay too much attention on the icon that it identifies your account, then you're uploading your private stuff into the attacker's account, and so on and so forth. And as I told you, this is essentially really similar to the session swapping problem that we have seen before. So the attacker is running the protocol, and it stops after authenticating. And then he puts, if you contact the attacker website, you're just redirected to the relying party, in this case Gmail, and the contents of the messages are the SAML response and the relay state URI, which can be used to perform to complete the protocol flow. So essentially, the problem of the Google implementation is a lack of contextual binding between the step 2 of the protocol and the step 4, because essentially the SAML response parameter and the relay state parameter are the only things that are necessary to complete the protocol flow. We have disclosed this vulnerability to Google on the 4th of February 2018, and we have received a bug bounty, which allowed us to come to RuCTF last year. And on the 25th of April, Google published a blog post talking about a more secure sign-in flow for Google applications. And essentially, the interesting thing is that they've decided not to fix the vulnerability on the server side, maybe due to some compatibility issues, but they have extended Google Chrome in order to track the execution of the protocol and warn the user that the authentication inside Google is taking place. So essentially what Google has done is somehow, let's say that they are confirming that using browser monitoring techniques is efficient to solve this kind of attacks. The bad thing is that if you're browsing the web using a browser which is not Chrome, so even Chromium, their implementation is still vulnerable. So you are still open. So summing up, doesn't work anymore. Does it work? Yeah. Okay, let's finish with this. So summing up, I hope that with this talk I've proved that lightweight policies on the client side are sufficient to enforce provable security guarantees in web protocols, but our work is not finished. In particular, we would like to support additional protocols that require enhanced security like e-payments. We would like to explore whether there exists some automatic techniques based on machine learning or something like that to synthesize the policies for WPSE starting from protocol specification or the browser traffic. And finally, since we have received interest on our solution by several parties, we would like to explore whether we can embed WPSE into real browsers. So this is it, and thank you for your attention, and if you have questions, please go ahead. No question? Well, okay. Thank you.